Hello. Okay, awesome. So hi everyone, I'm Thibaut. I'm working for Graphistry, and I'm going to talk about, at Graphistry we're doing visualization for very big data sets, and we use GPU actually to be able to process more data. So I'm going to talk about how we use and leverage the power of GPUs to make our code run faster. So let me start by motivating cool things that you can do with GPU. So this is a system from Otai that will actually record a hockey game, right, and then lets you live it, right, if you want in VR, where you can just see the game from any angle, be in the field literally, and this is all powered by GPUs. Another example actually is doing machine learning on GPU. So this comes from analytics, which has a whole platform for doing medical diagnosis, right? And they're actually, for instance, on radio, on X-rays, they're better than doctors to detect hairline fractures, right? And to get to that point, they had to learn, right, on a huge amount of data. And for that, GPUs are great. And the last thing I want to show you is actually what we do at Graphistry, which is building a data explorer for very large data sets. So let me show you a demo of that. All right. So I quickly hacked it up in Python, so you may not be, yeah, maybe that's more readable now. The code doesn't matter. What I did, I took all the speakers at this conference, and I look at who was following who on Twitter. And I made a graph out of it, and this is what I got. Let me reload. So this is our community of speakers. So we can see that I have two main clusters actually, you know, where most of the speakers are here. And for instance, over here we have the data visualization crew, for instance, and actually Miles just gave a great talk about designing data visualization with interaction in mind. So it looks like the community is actually kind of split in two, but that's not really the case. When I added to the graph, to the node diagrams, also all a link between speakers whenever they had a common follower. This is the picture we get. Okay, looks like the network is failing me, so
disconnect and reconnect here.
Okay. So this is the graph I get, and this is the raw data. So what I'm going to do actually, I'm going to run a clustering algorithm on the server that's going to be on a GPU, and that'll actually oh, looks like my computer died. No. What's happened? Let's try one more time. All right. Okay, I think my laptop died. Okay, well, so I can't quite show you the graph. In the past, recording the screen and running the visualization at the same time has proven to be a problem. So this is what you would see actually, in fact. So you see connected communities of all the speakers. The point here is that we run all the expensive analytics on the server, on GPUs, and then we stream the data to the client so that we can explore it. So this is what I'm going to talk about. I'm going to quickly give a high-level difference of GPUs and CPUs, explain what they're good at. I'm also going to argue about why you should care about GPU now, even though they've existed for like 20 years. And then we're going to, since this is forward.js, we're going to go, I'm going to explain how you can take advantage of GPUs from JavaScript directly. All right. So this is a CPU, what you have in your laptop and phone, and this is a GPU. So already at a very high level, we can notice a big difference, right? The CPU has a few processing units, but they're very flexible, and I'm going to explain what that means. The GPU has a lot of them, but they're very rigid, right? And again, I'm going to elaborate on that. But you might wonder, right? Why can't I get a lot of flexible execution unit, right? That would be the ideal hardware to program. Well, if you were to do that, your computer would burn down, right? So the key reason that drove the difference in designs between CPU and GPU is simply power constraints. We can put a lot of transistors on a chip today, but we can only light up so many before we just melt down the whole chip. So if we go back to the future, in 1995, this is the way your CPU worked, right? So here we have a program that's going to add a bunch of numbers, 4 of them. And the CPU is simply going to go through the program operation by operation, one by one. So we're going to execute the first addition, then the second one, and so on. So this architecture is called single instruction, single data, right? Because I apply one instruction on one piece of data, one by one. And you can see actually doing the operation, right, actually computing things is not what is consuming a lot of energy, right? Decoding the instruction and moving data around within the CPU is where we actually burn a lot of power. So fast forward in times, today, in your laptop, in your phone, your CPU is looking like that. So if we run the same program, it would just take the four in operation we had and just run them out all at the same time. So that's great, right? We go 4 times faster, but in terms of power, we're just consuming just as much as we did before, right? So this is called MIMD. We run multiple instructions, and each instruction operates on data independently. So there is actually another way in architecture and chip design that you can go to get better performance, and that's what GPU do. So instead of running one instruction on one set of data, they're going to run the same instruction on multiple pieces of data, right? And now that makes our life, us programmers, much more difficult, because to program such chips, I have to arrange my code to group operation together. So I do 4 addition, and then I might do 4 multiplication, and so on. In terms of power, that's a big gain, right? Because now I only pay the cost to decode the instruction and to execute it once. So that means I get to amortize all that cost that I had to move data around. So you know, this is why GPUs can have a lot more execution unit, is because they're more rigid in the sense that they need to do all the same. They need to do the same operation over and over again. So I said GPU have existed for 20 years, and that's true. They're in your phone, they're in your laptop. So what has changed in the last few years that you might want to take advantage of them? Well, sorry. WebGL? Not quite. So what has changed is you can now have GPUs on the server, right? In fact, you can rent one on Amazon for 65 cents an hour. And so that's a lot of computing power that you can use for your backend application that in the past was only available for gaming, basically. So, for instance, this is how we take advantage of GPUs in our architecture to do big data analytics. So we have GPUs on the server, and there we run everything that's computationally expensive. So for us, it's all the analytics, right? And then we stream the result to the client. That's simply over the internet. And here on the client, we use the GPU too, but this time it's only for rendering, right? And then we get to display the results. All right. So you may wonder, right? Why do I care to get the results so quickly, right? So let me here quote Marissa Mayer. So she said famously that for every half a second of delay in your web app, you lose 20% of users. So at Graph History, we build data visualization for security. Here you're seeing a data centers. So for us, the time to graph is critical. That means we need to be able to grab the data, process it into a visualization in a few seconds. And GPU enable us to do that. So if I were to run a visualization on CPU, this is where I would get after 2 seconds. So this is my data center, and it's a mess, right? There is everything is together. This graph is just not legible. It's a hairball, like we say. If I run it for the same amount of time on a GPU, this is the visualization I obtain, right? So all the different clusters nicely separated. Suddenly I have a graph that's legible, and I can just go about, maybe drill in, you know, one of my service, see what happens, see where the outage is. All right, so hopefully at this point I've convinced you that GPU are awesome. So the next part of the talk is just how do we use them and how do we use them with JavaScript. So if you want to do graphics, so if you care about rendering, we've had a lot of WebGL talks, and I would point you to them as a reference. For everything else, and I want to mention that there's some great library for JavaScript like 3.js. If you want to do anything else with a GPU, anything that's not graphics, unfortunately the situation here is not so great. So there is no nice high-level API that you can use to program a GPU. What you have to do actually is use low-level C-like API. So that would be OpenCL, sort of an open standard. And then if you use NVIDIA hardware, that would be CUDA. So at Graph History, we use OpenCL. So let me tell you a little bit about OpenCL. So OpenCL is kind of like C. So that means that in your program, you have variables that are typed, and then all your memory is just one big array. So in JavaScript, you were used to have objects, right, that you can pass around in function. In OpenCL and in C, everything is just an index into the one big array that is your memory, right? So that's interesting because OpenCL lets you structure your memory into, here I've structured it into a 2D array. And then I get, the key point is that I get to run the same operation on all of the cells of my array at the same time. So that gives me huge parallelism, right? That's where I'll gain performance. So if you want, if each of the little cells of my array is like one C function or one JavaScript function that I'm going to call. So let me show you one real CL program, actually, so to make things concrete. So this is what the program should do, and I've written here in C. This is the CL program, the OpenCL program that is going to move Node on the screen. So it takes a 2D array as input, and then for every element of that array, I'm gonna add 2 to every element. So I'm gonna displace, if you want, the node by 2. In OpenCL, I'll write it like that. So I would simply specify that it's a kernel. It's sort of a jargon to say one program. And I have to make sure that my input and outputs are passed as argument, because function in OpenCL cannot return value. And then the strange part is that my loops actually disappear. They become implicit, because the code that actually changes the position is going to be run in parallel on all of the cells of my array. So that means all I have to do is figure out, which cell I need to operate on, and this is done with those like OpenCL primitive function. Here get my ID. So, if OpenCL is great and give us a lot of performance, why don't we use it everywhere, right? Is there a reason to use anything else? The answer is that OpenCL code is actually quite ugly and complicated in practice. So this is a screenshot of our own code, and you can see it's quite complex, and it's not easy to understand what it does or why it's correct, right? There is like complex loop condition, strange commanded lines of code. So I mean, the truth is that it's tough to write OpenCL, but it's worth it because of the performance gain. Thankfully, actually, the Node community made it very easy to interact with OpenCL and GPUs, right? With all the nice features they've built in for asynchrony, and I'm gonna detail that. So AMD actually wrote bindings called Not OpenCL that map all those low-level C function onto JavaScript function that now we can use. And what's great about it is that I get to write my server application mostly in JavaScript, so I can be productive. And for the tiny bits that are performance critical, I can go down to OpenCL and make those important code paths really fast. So, for us, we noticed that in our code base, everyone except the OpenCL hackers are completely insulated from our use of GPU. It's mostly JavaScript. So there is one big downside with Node OpenCL, is that to use one OpenCL program, it has a lot of bureaucratic code that I need to go through. So this is how I would call a function in JavaScript. This is how you call the same function in OpenCL, right? So that's not fun. So thankfully, we're actually building a wrapper around Node OpenCL that we call CL.js. And the goal is to wrap all that bureaucracy and hide it so that we can call an OpenCL program just like you would call a JavaScript function. For instance, this is how you create your OpenCL program. This is how you declare it. And then you can simply call it just like a normal function. The only key difference, perhaps, is that the input and output needs to be either typed array or buffer, right? Because those are going to be passed down to the GPU. One thing that I didn't mention is that when you run an OpenCL program, right, since it runs on a GPU, your CPU can do other things, right, at the same time. So that function that wraps your OpenCL program has to be an asynchronous function. So you get notified when the results are ready. And that's where Node is awesome, or the JavaScript in general, because it has all those great promise library to deal with asynchrony. So for instance, this is how I would, compose OpenCL program together, where I would, call our move node function to move the points, and then I might use the result and feed that into several other OpenCL programs. All right. One cool feature of CL.js that we implemented is code specialization. So let me explain you what I mean by that. In OpenCL, you often end up using macro because you really care about performance, and macro lets you target special device, optimized for a special hardware, and also it lets you enable and disable code path as needed. So that way the compiler only really sees the code that you need and can do a better job at optimizing it. So as a result, instead of passing a function, a parameter as a function argument, we often just pass it as a macro. So what it means is that when you want to change one of those arguments, you would have to recompile that OpenCL program every time. And we actually handle that completely transparently. So you can simply, if I disable the strong gravity feature, then I would run that piece of code. And when I change that parameter to true, then I would simply recompile my program, this time with this piece of code. And that all happened in the background without me, the JavaScript programmer, having to care about it. All right. One thing that would be great that we haven't implemented is simply take any JavaScript function, maybe a type 1 in ASM.js, for instance, and translate it to GPU code, right? So that it can be run efficiently on the GPU. So one cool stuff would be, imagine, for instance, taking a query from the user over your data set, say a SQL query, and instead of running it on the CPU, translate it down to GPU code and run that on GPU. So there is no big technical hurdle that prevents us to do that. We just haven't implemented it. So what we're really doing is really building the equivalent of jQuery, but for OpenCL inside our CL.js library. And we are actually, right now, we are actually busy porting it to the latest version of Node OpenCL, and we are hoping to release the library this summer. So if you want an early version of it, you can email me. All right. So the question that you may wonder, so we've done all that work to take advantage of GPU and gain performance. Was it really worth it? Well, yes. Here is the difference between a state-of-the-art, Graph Explorer, Gephi, running on multi-core CPU and our GPU implementation. So we get to be about 60 times faster by taking advantage of GPUs, and that lets us process about 15 times more data while remaining interactive. Right? That's very important for us because, again, by being interactive, by giving the user answer quickly, we follow a Marissa Mayer principle, and fight delay. Again, every half a second of delay costs you 20% of users. All right. So a couple of takeaways is that GPUs actually work very well with Node. So, take advantage of them. Take advantage of the fact that you can now rent one for 65 cents. And in our experience, we get great performance with it, and that doesn't affect our productivity much because we still do most of our work in JavaScript. All right. So that's it for the talk. We're actually recruiting UX, UI expert or InfoVis designer. So if you're interested, please come talk to me. And email me if you want to try out either our Visualization Explorer or the CL.js library. That's it.